Hey everyone, today we're going to be talking about Mecanum Drive, what it is, how to code it, and how to build a robot that uses Mecanum Drive, specifically for FTC teams. Uh, so Mecanum Drive, to be honest, it's pretty overhyped uh, in terms of how complex it is. It's actually very simple, and it's really useful as well. So here I have a quick diagram about a Mecanum drive. So usually when you have a car, you can do this, where you can go forward if your car is four-wheel drive. We're talking about four-wheel drive here. Your car goes forward like this, or your car can go backward. That's pretty simple. We're going crazy. Um, or your car can do some turning. Uh, Not you wouldn't really be turning in these ways, but you would have um, like your front wheels actually be turned. Uh, in this case, we're turning almost like a canoe, and this is what I think we're mostly used to seeing in robotics. Is being like this or like this, where if you want to turn right, you're going to have your left wheels go forward and your right wheels go backwards, and the opposite for turning left. But Mecanum Drive is different. Mecanum Drive allows us to strafe or crab walk, which is what we have here, here, and I'll explain the other ones later. And so this allows our robot to literally go sideways, the opposite direction um, of like the wheels are facing. This is because um, you can see on these wheels that there's these smaller wheels on these other wheels. These aren't in any random direction. They have to be in these specific directions. And when you're building your Mecanum drive chassis, your wheels need to be facing in these specific directions. You can see them right here. Uh, you should have your wheels facing this way, this way. Um, what would what would be this way, and this way. You can really just look at this diagram and copy that for your Mecanum drive. And because of that orientation, because you have these wheels on your wheels, it allows you to do some really cool movements. In addition to the strafing, you can go diagonally really effectively. And pretty much no matter what rotation you're in, you can go in any direction, which is really useful, especially when we're in a competition environment and like an FTC competition environment. And oftentimes we have to go through really small spaces and do some really interesting maneuvers. But because of uh, the complexity of these wheels, sometimes coding um, these wheels can be a big of a struggle. So here's the code that my team 8617, Techno Tigers, we're based in Melbourne, Florida, uses for our Mecanum drive. We use a super like simple Mecanum drive setup, just like the one that you saw before. And honestly, once you understand the basics behind this drive, you're going to be like, man, this code is also pretty simple. Uh, so just like every other uh, code, we're going to call all of our normal, we're going to import all our normal stuff. Um, then we are going to have define our motors. Um, and we have an elevator that we're also going to be talking about. With some servos that are also part of our code, not related to Mecanum Drive. We're going to, connect the motors that we just defined to the ports that we labeled as part of our configuration. And then we're going to start setting directions on these motors. Because of how wheels work, uh, if you look at like let's say we have a four-wheel drive chassis, uh, and it's four wheels on the chassis. Forgive my drawing skills. So these ones are going to rotate this way further forward and this way further forward. But these other ones are obviously going in the opposite direction. And so that's why we have to reverse this set direction here. Simply reverses uh, the direction of these motors. So now forward is this way for these motors. So now they're all forward together, which of course makes coding much easier. We also have some other stuff for elevator and servos that are unrelated to this. And now, just as in any other code, this was all post initialization. This is going to be stuff that happens after we hit the start button. Now we're going to run the actual part of the code that makes Mecanum. So the first thing we're going to do is we're going to calculate the hypotenuse of left stick X and left stick Y. So we're going to be using our left stick mostly to steer this robot around, and the hypotenuse, if you take in like trig and stuff, is going to be the angled sort of slope of the triangle that the x and the y make, giving us like an actual direction, an actual single vector, instead of, I mean, I'll just illustrate this for you. Like this is our x, this is our y. We're going to get this guy here, which is, very useful, because that's the real direction that this is going to be in. Then using that, we're going to find the angle that our little like hypotenuse is at. So we're going to find this angle right here, which it is going to be useful later on. We're going to subtract it by pi over 4, just so it like goes in the right direction that we want it to. Not just some like logistical stuff. And then we're going to define our variable for our right stick X, which is actually going to play an important part in this robot as well. I'll tell you. Well, we're about to get into that, what that part that is. So here we go. So we're going to start defining what power to give to each of those motors, because yes, we know what direction we want to go in, but we really need to know what to tell our motors to go in those directions. So V1, 2, 3, 4 are different motor directions. R here is the hypotenuse that we calculated earlier. You can think of this as the magnitude of the vector, the absolute value of the vector, which is really the how strong, how are we pushing this joystick all the way forward, all the way backward? Are we pushing this joystick, or are we pushing this joystick all the way forward, or just a little bit forward? That's what this magnitude here, these magnitudes here are. Then we're going to multiply that by either cosine or sine of the robot angle. So this is the robot angle that we have calculated. Cosine would give us, like this is, so Katoa is going to give us the adjacent side, which is going to be this side right here. The sine is going to give us, the sine is run. The sine is going to give us this side, or the opposite side. And we're going to call different ones of these based in which motor is where. And then we're either going to add or subtract the right x value. This is like a whole bunch of math, if I'm being honest. And like, it's not like you can pretty much take this math and put it into your code. But I'm going to do my best to try to explain it, even though it is kind of weird. Like trig is just generally a bit annoying to explain. So let's get into this. I'm going to ignore this first, what we have inside our if statement here for now, and I'm just going to get into what we have sitting here. And so what we have here is so that left stick that is as I told you earlier does most controlling. We're going to push that left stick, and so now all of our motors are going to get power. You can see there is our front left, front right, back left, back right. Motors are going to set power. You can see they're all multiplied at 0.75. That's just a personal preference on our team. We're slowing them down a little bit, um, just because that's easier for some of our newer drivers. Um, and then we're going to multiply them by these powers that we calculated them earlier. You'll see that these aren't in order for me. That's because I switched them up when I was using this code, and you may need to switch which of these are in which place, um, which could based on which motor they're powering, and then what your personal configuration looks like. So you may need to change which of these powers is going into which of these motors. Although it's really not that difficult. You're just going to switch them around and really see what works. Or you can kind of do the math and follow along with me here. So we're going to put V2 here, the sign minus right X into our front left. And then we're going to put V3, which is our sign plus right X into our back right. After that, we're going to put V1, which is our cosine plus the right X, into front right, and our V4, which is cosine minus right X, into back left. So we're just taking these powers, and based on the input that we put into our left, we are going to give them power. But also, the input that we put into our the right is also going to play an important role. You see these minus and pluses? That's because while we will control the direction of where the robot's going, so let's say this is our robot, we can either make it go this way, or this way, or this way, or this way, or even diagonally. We're going to control this with our left stick. We're going to actually be able to do some like turning in terms of rotating with the right stick here. And so that right stick is going to have effects on how that works. Next, we're going to talk about turning while not moving. So you'll see in the if statement that we have here, this is just taking in left stick inputs. So it's saying if we're pushing down the left stick, do these things, set these powers that we just talked about. And you'll notice that it's greater than 15 or less than negative 15 in the y direction, and same thing for the x direction. That's really just sensitivity control, because if this is pushed less than 0.15, maybe just pushed by accident. And so this is really just sensitivity control. But let's say now we have an if statement here. If we're not pushing this, so assuming that we're not trying to move the robot in any real way and it's stationary, we want to turn the robot left or right. This is our robot, and this is wheels. Once again, excuse my drawing skills. We want to turn it left or right in place. We're going to use our bumpers on our controllers to do that. And so if you press left bumper, it's going to turn the bumper. Press right bumper, it's gonna turn the robot. Sorry, it's gonna turn the robot. You can set these to 1. You can set these to whatever power you want. We just chose to set these at 0.5 power here. You'll notice that it's turning. So one side's gonna be set to positive, while the other side's set to negative. See in both these situations. Then you'll notice we have some stuff here. So this is a good point in illustrating the difference between a Boolean and a scalar. So these bumpers on our controller are either off or on. You're either pushing them or you're not. This is going to give me a true or false value for this if statement, conditional here. And then This if this is true, then you do this. If it's false, we don't. These, however, similar to the joysticks, these triggers are not. They're scalars. We can either push them a little bit or a lot. And so, one, we want sensitivity control. So if you push them a very, very little bit, it shouldn't do anything. But two, it allows us to have a little bit greater control because we can choose if we want to do a little bit or a lot. Our driver can choose their mecanum. And so these triggers, these two trigger things, turn us right or left, um, actually do the same thing as our bumpers here. But because our drivers wanted a little bit more control over um, how they turned the robot, they we made these little trigger parts so they can control uh, just how much they're turning. And then finally, uh, we have this else here that says if we're not pushing any of this other stuff, not pushing the bumpers or the triggers or the joysticks, everything should be set to zero, which is fair. The rest of the stuff here is just about some servos uh, and elevators, which isn't related to what we're doing. But comment below if you want some videos about the other stuff that we do, and maybe some videos about servos and elevators and different um, manipulators and other mechanisms like that. Um, but hopefully you got an idea about what a Mecanum drive is, how it works, how it can be super useful in FTC, um, and uh, how you could possibly code it. This code will be available in the description. And thank you for watching, and good luck.